Good morning, everybody. Welcome to Richmond, Virginia. I'm Jeremy Hoffman. You kind of caught me actually in my burning hat phase. I am between jobs right now, actually, which is incredible. For the first time in my career, where I was the chief scientist, the David and Jane Cohn scientist at the Science Museum of Virginia, where you will be having your social event tonight for about 7 years. And on Monday, I start as the Director of Climate Justice and Impact at Groundwork USA. So I am in the in-between time, and I get to talk to you about some of the great work that we've done here over the last few years. And I wanted to just start off by saying, this is such a unique event here in Richmond. I'm so excited to have you all here. I want to give a shout out to several of my colleagues that are in the audience. Very, very cool to have a lot of familiar faces. And thanks to the OSM team for giving me an opportunity to talk to you this morning. So I also serve in a capacity as the chapter lead for the Southeast chapter of the National Climate Assessment, which will be published in sometime around October or November. If you've not heard about the National Climate Assessment, I'll talk to you a little bit about it today, but I'm not going to share too much about our maps that we put into the chapter today, but you'll have the chance to learn a little bit more about that in the near future. I like to start my talks by embarrassing myself. Other than the absolute, fashion sense that is coming full circle, we are 2 weeks away from kids walking around in that outfit again. I am sure of it. It's also, you can't quite see it in the picture, but the hair, I had my head shaved, but my bangs were still there. Called the pineapple haircut to some of my friends. But the really important part of this picture, other than the early adoption of flood pants, adaptive capacity to climate change there, is the fact that I'm a fisherman. I grew up fishing with my dad in the lakes of northwestern Wisconsin, an hour south of Duluth, Minnesota. And so I spent the better part of my childhood learning how to observe the natural world and make predictions about things related to fishing. And over the course of the last 30 years, 35 years actually, the amount of particular fish that we would go for, a bottom water feeding or bottom water living fish called a walleye. It's delicious. My dad used to make walleye and eggs for breakfast. I swear it's good. It sounds bad, but it's good. Those, over the course of 35 years, have declined significantly in their reproductive success, and that has been tied directly to the impacts of a warming climate from climate change. So I come to this work in climate change as climate change really threatens my identity as someone that enjoys the outdoors. And I hope that you too can take on some sort of relationship to climate change in the sense that it threatens our intergenerational kind of sharing of cultural events. And anyway, that's who I am and why I show up to climate change research and how I got involved in some small way with the work that I do today. So climate change, as you know, brought on by the accumulation of heat-trapping gases in the atmosphere from human emissions of heat-trapping gases from burning coal, oil, gas to power our society. And almost every single year in the last 10 years is among the 10 warmest years on record. And we expect this to continue as long as we continue to burn fossil fuels. So really the biggest uncertainty in the future is not at all about what's going to happen in the climate system. That's just physics. The biggest uncertainty in the future is what we decide to do in like the next 10 years. So again, the biggest uncertainty in the future of climate impacts in this country and around the world is what we decide to do in the next 10 or so years. So it's not at all about the uncertainty in the climate system, it's the uncertainty in the human system. And we know that climate change impacts us in various ways. Here in the United States, we have a kind of scaled down version of the IPCC reports called the National Climate Assessment. The last one was published in 2018. You can read a whole bunch of really cool stuff in that report, from regional chapters that focus on particular places in the United States to individual topic areas, things like the economy, transportation, and public health. And really, I can distill the hundreds and hundreds of pages that are in these scientific assessments into 5 emojis. We are already experiencing and expecting, due to future climate change, a hotter, wetter, sneezier, and wheezier climate. So we're going to talk a lot today about the hotter sense. Wetter, sea level rise is happening faster here in the coastal part of Virginia than anywhere else on the east coast of North America. Precipitation becoming more and more flashy, producing more opportunities for flood. Sneezier and wheezier, longer, stronger pollen seasons. Our pollen season here in Richmond has gotten 25% stronger and 2 weeks longer since the 80s. And then wheezier, we all saw the amazing pictures that came out of New York City, which were just another continuation of the pictures that we saw from the previous year in California, and how events thousands of miles away can have a direct impact on our air quality here in the east, on the East Coast. We actually had the worst air quality day from particulate matter in the observable record yesterday. But we also know that the decisions that we make about how we design the natural or the built environment around us has an influence on those background climate stressors as well. Some things like how we decide to do building density, layout, height variability, how we operate our human systems, and how we build those human systems can actually push climate change to be more intense in the sense of heat, while the things that we like about natural areas, vegetation, and things like lakes and seas and rivers actually can lower a city's temperature. We're going to talk a lot about this today, so I wanted to make sure that I touch on how the built environment and how we design our human spaces can have a direct impact on the temperatures that are experienced, because we know that heat is the #1 killer of weather-related hazards. It might come as a surprise to find out that heat kills more people than any other of these weather-related hazards in the country, even more so than things like hurricanes, which I think there's a reason behind that. If you think about hurricane season, what do we do with hurricanes? You can see them in satellite imagery. You can see them move across a landscape. We give them names. It's really easy to be like, Augusto, and then we send, reporters out into the streets to be like, I'm out here at Main Street. Whereas with heat, we have a really hard time describing the threat. And that's why it's sometimes called the silent killer. It has different thresholds for different people. People with chronic illnesses are more likely to have a heat-related illness than those who are healthy. Elderly and very young people more likely to get sick due to heat. And then regionally, depending on where you are, someone from Miami has a very different tolerance to heat than someone from Duluth, Minnesota, because of where they live latitudinally. So the intensity of heat, the thresholds that we use to describe extreme heat are all different for different people in different places. So it's very difficult to describe and actually communicate that risk. So we've been working a lot to understand how heat is inequitably distributed among our neighborhoods for many, many years. And probably the lesson that we learned or didn't learn, depending on how you look at it, comes from the city of Chicago, 1995. It was over 100 degrees for several days in a row. It didn't get below 80 degrees overnight for 3 nights in a row. And Eric Kleinenberg kind of did the first real social deconstruction of this kind of natural disaster in his book Heat Wave. Pretty good name, where he showed that not only, there was an estimate of 750 people that died in this heat wave, but it was really important about who they were and where they lived. And what he showed was that elderly members of communities of color, particularly on the city's southwestern side, that had experienced intergenerational marginalization economically and socially, were dying at much higher rates than other neighborhoods made up of similar populations. So there's, again, something here I want to preface is that the inequity of climate change is separated by neighborhood, so much so that we can pretty much predict your vulnerability to a climate stressor by just looking at your zip code. Now, we also know that not only are these impacts inequitably distributed, but the stressor itself is inequitably distributed. So we're going to do an exercise here. The whole classroom has now become the magic school bus, and I am Miss Frizzle. We're going to fly into this picture, and you are going to go to the hottest place to the touch. You are going to find the hottest spot to the touch. And on 3, you are all going to yell it out loud so that none of you feel embarrassed about having the wrong answer. All right, so on 3, what is the hottest spot to the touch? 1, 2, 3. Amazing. Okay, it was just like, blah, that's what it sounded like up here. It's a very good guess. Blah. How about on the opposite side? What's the coolest spot to the touch? Where are you going to the coolest spot to the touch? On 3. 1, 2, 3. Now that one has way more consensus. Almost every single time I've given this talk. I've given this talk 100 times. 150 times, and almost always, shade or trees is the thing that I can pick out the most from that second guess. But the first one, you have a whole range of different ideas. Now, what's amazing is that, and to speak to Dr. Schwartz's comments just a second ago, is that we can actually use citizen data to understand this landscape, to actually show us and match the hottest spot to the touch with the temperatures that those surfaces experience. In fact, it's called a FLIR camera that I can put on my phone and take a picture of this very same environment and reveal the temperature variations to the touch. These are surface temperatures coming off of these different surfaces. The brighter colors are the warmer temperatures. If you guessed the asphalt, you were absolutely correct. Those have very low albedo or reflectivity to the sun's energy, so they absorb more and then re-emit that energy back into the atmosphere as heat throughout the afternoon and into the evening. Meanwhile, if you said trees, you were 100% correct. There's, to the touch, about 100 degree Fahrenheit difference between these two places. But what's amazing to me is everything in between. The choice of our vegetation has something to do here. So these are non-native European grasses, or lawn, as we like to call it. It's the same temperature as the sidewalk. These are native plants that evolved here in Virginia. They have much deeper tap roots that can get to groundwater much more efficiently than these non-native, very shallow kinds of grasses. Look at the different cars, all the colors of the cars. Again, reflectivity to the sun's energy. This one photo, I can teach an hour-long class about how you could use this information to then design a city that actually lessens temperature versus amplifies it. And I see your hand raised. We're going to hold questions until the end. Thanks. But we know also that the temperature to the touch doesn't directly correspond to the temperature that if you were walking through this environment, you would not feel 170 degrees on the pavement, and you wouldn't feel the 87 degrees underneath the big shady tree. So we need to come up with better ways of mapping how temperature varies across urban environments. And my colleague Vivek Chandas back in 2016, 2015, actually figured out how to do this, borrowing some ideas from early 2000s and 2009, David Saylor's work in Portland, Oregon, where he figured out we can just put thermometers on cars, and at the same time as taking measurements of the air temperature, and now we're measuring humidity, we can also take measurements of where we are using high-resolution GPS units. So he came up with a way to basically distribute scientists all over a city at the same time during a heat wave, taking measurements of temperature and place. Now, what we did here in Richmond was to include the community in the development of that methodology. So instead of scientists doing it, we recruited volunteers from different organizations throughout Richmond, including Groundwork RVA, which is the local groundwork trust that is part of the Groundwork USA network. And we actually worked together in a kind of consortium way to decide where we were going to go and how we were going to actually distribute ourselves around the city. In July 2017, we captured an extreme heat event. I rode my bike, which was very unsafe. We go out at 6 a.m., 3 p.m., and 7 p.m. in order to measure the coolest, warmest, and then evening temperatures in a day. And then by taking the information of all of these observations going around the city, we can then relate it to land use information at the same time, and then build a physical model to actually infill places where we didn't take direct measurements, but have similar types of land use underneath, and then increasing buffer zones around that. So we can actually then create very highly predictive surfaces of how temperature varies. And in fact, in Richmond in 2017, we found a 16 degree Fahrenheit difference between two places at the exact same time. In the heat of the day, 16 degree Fahrenheit difference. Now, If you're not familiar with the city of Richmond, many of the places that you see that stick out as red are our formerly industrial areas. Scott's Addition, which you'll be next to this afternoon and evening at the Science Museum. We have Manchester and the south side of Richmond here, and then the East End. This is Church Hill. Many of the coolest places had very high amounts of tree canopy. And interestingly, this is downtown. Downtown had a lot of varying temperatures because of the height variation in the buildings. So we can actually see cool canyons created by the shade cast by those buildings. Now, you might be asking, what's the impact of this on the city of Richmond? We actually then worked with the ambulance authority to map where they go for heat-related illnesses. And on the right, that is a density map of basically where they go the most for heat-related illnesses during that same time period, 2015 to 2018. We're working on this follow-up with a student at the University of Richmond to understand this in more detail. But what's really important too from our lesson from earlier in Chicago was we need to disaggregate that by not only where they live, but who they are. We find the exact same type of story here in Richmond as we did in the data from Chicago, where Black residents of the city of Richmond are showing up disproportionately in the heat-related illness responses from the ambulance relative to their citywide population when compared to the white community. So this is a clear environmental justice issue in the city of Richmond, and we've done a lot to work on understanding not only what we're going to do in the future, but why that is. So very quickly, one of the things that we noticed pretty much right away was how, and many geographers and human geographers have known for a long time, is basically any city, any map of any city is virtually the same map of like everything. You know, all of the socioeconomic maps that you can make are basically the exact same in like from food deserts to vacant lots to poverty. They all kind of look the same. And so we've been searching for these kind of unifying urban planning decisions that were made to kind of try and explain this. One way that we've come up with that is to look at these redlining maps. Now, Rob Nelson from the University of Richmond is here, and he is probably the person that, if you want to learn more about this, he produced the Mapping Inequality database, where you can go and find all of the redlining maps from around the country. This one's the city of Richmond's. If you're not familiar with the practice of redlining, very quickly, it was a way of basically trying to assess the security risk for financial investment for particular neighborhoods, but really it was about the color of the skin of the people that were living in those neighborhoods. In Richmond, for example, Jackson Ward, which was the place, basically the Harlem of the South at the time, the first woman-owned bank, Maggie Walker, was in this neighborhood in Jackson Ward. But instead of actually remarking about the black wealth that was in this neighborhood, they were just referred to as 100% Negro. That was the only thing that was descriptive about Jackson Ward. Meanwhile, over here, this is Windsor Farms. You probably won't go there during your visit, but if you do, come back. Agecroft Hall is in Windsor Farms, which is a castle that was taken apart brick by brick and then reconstructed here in Richmond, piece by piece, again in Windsor Farms. So this is exceptional wealth in this neighborhood, even in the present day, and at that time, they were referred to as the best people. So when we talk about redlining maps, really it was meant to be about financial security, but was really mostly racially motivated. And we see in the economics literature that these redlining maps had huge generational impacts on the socioeconomic measures of success for people growing up in these neighborhoods. So this is like multi-generational cohort level impacts. So we wanted to find out more about how the built environment related to the present day urban heat island stuff that we were assessing in many cities. And so when we look at the quality, the kind of environmental descriptors used for these neighborhoods, these are the A and B neighborhoods. What you see right away: wooded, shade, golf. Almost every wealthy neighborhood is placed right next to the country club in many American cities. But you can see already at the time of these maps in the 1930s and 1940s, these areas had much more environmental amenity at the time versus their redlined and C-graded counterparts. They were already referred to as paved, hot sewers. We would recognize those descriptions today as environmental justice communities, but at that time, that was how they were being described in their environmental makeup. And if you want to know more about how this actually plays out earlier, because redlining isn't the only thing that ever happened, Stephen DeBerry gives a really amazing TED talk called "Why the Wrong Side of the Tracks is Usually the East Side of Cities." Highly recommend that. Exploration of residential sorting. So our research in 2020 was published about how these redlining maps relate to extreme temperatures. It was published in the journal Climate, but the New York Times published it on the front page. Nadia Popovich did the cartography for this, showing our data for Richmond. Those formerly redlined neighborhoods are not only warmer than their non-redlined counterparts during the summer, but they have much more paved over surfaces, those same surfaces that you identified in that picture earlier as being the driver of those temperatures, and many fewer trees. I'm going to share some more data that has come out recently, but basically the big take home from our paper was that in 94% of the cities that were redlined, this pattern was observed. So almost without fail, redlined neighborhoods and communities across the country are physically warmer during the summer than their non-redlined counterparts. This has huge cascading potential impacts on their energy burden, their health, and other climate-related stressors, as many follow-up studies have found. Actually, Ross Donahue at Esri did this really interesting thing, taking LiDAR data about tree height, showing that not only were these formerly redlined areas have fewer trees, but the ones that are there are physically smaller. So they have probably less room to grow, they're probably different species, and probably have higher mortality. And actually a follow-up study from the city of Baltimore showed that to be true, at least in the city of Baltimore. So this is interesting. Across the country, we find this exact same kind of trend in their size. If you're familiar with the First Street Foundation, they've put out a bunch of these risk factor maps. This is their flood factor map. Anywhere that's blue has an underestimation of flood risk in the FEMA maps. Unsurprisingly, formerly redlined areas have much higher parcels with high flood risk than their non-redlined counterparts. So not only is it hotter, but it's wetter. This was actually picked up by Redfin, the website where millennials go to dream about home ownership. And you can see that the breakdown between the differences here vary by city. We're following this up with some study at the Richmond Federal Reserve Bank actually right now to see how much exactly we can attribute to redlining. Now, it's not just hotter, it's not just wetter, it is also sneezier and wheezier in these formerly redlined areas. A study that came out just last year showed that formerly redlined areas have significantly higher amounts of NO2, which is a principal component of the EPA's air quality index, and this is largely explained by the fact that following redlining, the federal transportation federal transportation projects basically then bulldozed redline communities to then become where the interstate system would go. So here in Richmond, Jackson Ward cut in half by I-95-64, and we're now working on trying to put a cap park over the over 95, as though that provides any sort of generational salve to this treatment. So, and this pretty much doesn't fail anywhere across the country. Leading many researchers now to kind of summarize things into these long-winded charts. This is not a map. If you're not familiar with this is a flow chart. But basically it shows how and why these sorts of intergenerational disinvestments in things like redlining then lead to the health disparities and environmental disparities that we see in the present day. So much so that the literature continues to grow, but redlined areas tend to have higher amounts of asthma. That's, again, that proximity to traffic that's probably there. Cancer, these are also places that were paved hot sewers, remember? So you're right next to other forms of environmental injustice in the types of emissions that might be around you. There are higher amounts of COVID-19, gun-related injuries, preterm birth, chronic diseases, and heat-related illness. So, I want to say, and I think I pretty much need to wrap things up now, but our neighbors in many cities across the country were already experiencing a hotter, wetter, sneezier, and wheezier environment than others. So when we talk about how these urban communities and cities around the country are going to be adapting to climate change, we need to recognize that there is this already existing, even without climate change in the room, even if climate was not changing, there are these existing environmental disparities between neighborhoods in our cities that are amplified and made more acute by a changing climate. So I would love to be able to tell you more about what we've done in Richmond over the last few years, but come find me later. I'll try and come by the Science Museum tonight. But in order to stay on track for the time today, this is, I guess, where we'll stop for now. So thank you very much for your attention. I appreciate it.